we showed, if you remember, that we can actually integrate the ES component. So if you take the ES component and integrate that along the streamline from a point like S1 to a point S2, we showed that you get some interesting form, which is an expression such as this. Integral from 1 to 2 rho dvs dt, all integrated along a streamline with element of integration ds, plus p plus half of rho vs squared plus rho gz, calculated at station 2, minus p plus half of rho vs squared plus rho gz, all calculated in a station 1. This net sum should be equal to 0. And if I put this in a red box, or magenta box in this case, you all should be able to remind yourself what is this equation. This is the general unsteady form of Bernoulli equation. And it simply tells us that there are some transient terms that come due to the unsteady nature of the flow, and we need to integrate them along the entire streamline. But if the flow is a steady state, we can ignore them. And what we will have is pressure plus half rho v squared plus rho gz should remain constant as we move from one point to another point on a streamline. And this idea that pressure plus rho v squared with a 1/2 prefactor and rho gz should remain constant, as we said, comes when we integrated the force balance along the streamline. So when you have force and you integrate it with length, you get energy or work. And this is nothing other than a statement of balance of energy. The overall kinetic energy of fluid elements plus the potential energy in the gravitational field and the energy that is stored in pressure should remain constant if there are no viscous forces acting on them. So as we discussed, there are certain important underlying assumptions in this derivation. We assume that we have inviscid flow of an incompressible fluid and the other important thing to keep in mind is this is all done along a streamline. And especially when we are thinking about using the unsteady form, which is having this term non-zero, we need to be extra careful. We can only use the unsteady form. The flow may be transient, but the shape of a streamline over which we have written this equation and integrated it, the shape of that specific streamline should not vary with time. That shape should remain constant. That geometrical shape should remain constant with time. That's one big condition that we need to keep in mind. The normal component of Euler equation gave us some interesting physical intuition too. We understood that if we have, for example, certain streamlines that are curved, if, for example, I look at the typical streamlines of flow in a hurricane or ideal vortex, as we discussed extensively in the class, we notice one thing that is very interesting. At the center of rotation, pressure takes its minimum value, and as I go normal to these streamlines, pressure increases to larger and larger values. So you have a gradient of pressure field that comes due to the centripetal acceleration. We saw the consequence of this in many different applications. For example, going back to the example of rigid body rotation, indeed we saw that if we have a tank that is going through rigid body rotation, one way of thinking about why we get a parabolic profile is the fact that if you look from the top, all the streamlines are curved because everything is rotating here. So this is the classic example where you use the cylindrical coordinate system R z, and things are rotating in the theta direction with an angular acceleration omega. So v theta turned out to be r times omega. And we notice that in this case, indeed, we have the fact that centripetal acceleration gives rise to higher pressure at points that are further away from the center, and that would give rise to a increased pressure that should be compensated by the rise of the liquid column on its top. That's why we get a parabolic profile. Exactly similar kind of shape of streamlines, circular streamlines, show up when we looked at the problem of ideal vortex, which happens when, for example, you have a tank and at the center of it, all of a sudden you open an orifice, and with some initial angular momentum, you let the fluid elements get out of that central drain. And we notice that again, we used the concept of cylindrical coordinate system, RZ theta. And here, V theta was constant divided by R to conserve angular momentum. And again, we saw that being further away, you get a larger pressure. That's why the profile rises to a higher value. But since the kinematics and the change in velocity is dramatically different between the two, the equation that you see in parabolic, the parabolic equation that you see for the profile in rigid body rotation does not repeat itself for the ideal vortex or the drainage problem. And you get a different profile, which we studied extensively. Now, these were nice applications of Euler equation normal to streamlines. Euler equation parallel to streamlines, again, remind ourselves, gave us Bernoulli equation. And Bernoulli equation was something that we extensively used in certain interesting problems. One interesting problem that we studied was the case of a tank that has a certain liquid inside with a certain large height h. And we ask ourselves what will happen if we open a small orifice at the very bottom of the tank. And you can imagine that the large hydrostatic pressure will force the liquid jet to come out. We use Bernoulli to show that the velocity of this jet is a result that is known as Torricelli's result, the square root of 2gh, where h is the height of the free surface compared to the orifice. We also saw that this is the steady state case of Bernoulli. But if we like to look at, for example, a transient process where the orifice is not short but rather long, so this is a long pipe that at one end, so it has a length that goes as L, that at one length is closed, and all of a sudden at time 0 we open it, we saw that velocity is not anymore the square root of 2gh. Velocity of the jet that comes out of this transient problem, where the pipe is closed and all of a sudden we open it, asymptotically reaches a square root of 2gh, which is the steady state result if we wait enough in time. But at early times shows a linear increase with time, and we found that this can be captured by the tangent hyperbolic function, and this all came from solving the unsteady Bernoulli equation for this problem. So as a short summary, we saw that Euler equation can be used in streamline coordinates in both parallel to streamline and normal to streamline components. The normal to streamline components became very useful in places where streamlines show a certain curvature and there are parts of a circle or maybe a full circle. The Euler equation parallel to streamlines, when integrated, gave us a very useful principle known as Bernoulli principle. Bernoulli principle, it can be used and it can also be abused. We need to be very careful about the assumptions, the underlying assumptions for this principle. And we found out that in certain cases, we can apply it in a steady form, and very easily we can find a connection between hydrostatic pressure or height and velocities that will result by just using the principle that whatever potential energy fluid elements have here, it gets completely converted into kinetic energy as they exit the nozzle. But at the same time, if the flow is transient, but transient in a relatively controlled manner, where the shape of a streamline in a long pipe does not change with time. We can use this unsteady form and then find out what would be the transient behavior of the velocity. Initially, it grows linearly, and finally, it reaches its steady state value that is set by Torricelli result being a square root of 2gh. This is an overall review of how we really use the concept of Euler equation and applied it to many different problems that the acceleration term was not necessarily a simple or intuitive term to deal with. You can see that with a good, proper bookkeeping of different elements of this equation, we can actually solve many different problems. In the next video, we will switch to a new topic for this review session, which is mostly about contour volume analysis.